you added 3 plus 2. I'm saying a more complicated calculation. Because how the heck is it computing a cosine? How is it doing a natural log? How is it doing something that's irrational in general? I mean, think about it. How does it calculate irrational? I mean, there's got to be something in there. Well, a lot of it is actually series. And that's why there are questions you can ask that actually take a few seconds because it just took a little longer for it to do it. It's just doing it much, much faster than we can do it. But a lot of the calculations it does are not the calculations you would have done. So I love this example. This is a factorial manipulation. So if you knew, I'm not asking anyone to do this, but if you knew how to write a simple do loop, does anybody here know how to write a do loop? You've done? Yeah, write a do loop just for fun, say, 1 to 1,000,000, and then come back and tell me what 1,000,000 factorial is. And you'll say it's e to, now, you're gonna have to give me an approximation, give me as many decimals as you feel like. And now 1,000,000 factorial would be e to that number. Isn't that incredible? That is so powerful. Logarithms are a very powerful way of expressing things in general. I'll give you an example. Everybody here, how many have had chemistry? I'll use this. Okay, what is pH?
The log of the concentration.
It's a logarithm, isn't it? It's a logarithm generally ranging between what and what? Not a huge range, right?
0 and 12 is 1 and 12.
Well, it can be negative, can't it? It's measuring the base or the vicinity of something, right? It's a logarithm, though. Yeah, it can be negative. It's a logarithm. What is Richter scale?
Earthquakes.
That's us measuring the intensity of an earthquake. That's also a logarithm. Oh, so earthquake of magnitude 5 and an earthquake of magnitude 4, the 5 is exactly 10 times. But it's not a natural log, it's a log base 10. What is the decibel scale? That's sound. So those are the big three, if you didn't know that. I mean, I would teach us in a remedial algebra class. Richter scale, decibels, pH are all log base 10. That's literally the only use we have of log base 10 because that was standard. But every other logarithm is easy. What's scientific notation? You always write something times 10 to a power, so I need 2 different numbers. What if instead of using scientific notation, I just simply used log base 10? It would actually be a lot more convenient, wouldn't it? I'd only need 1 number. And by the way, so but what about the rounding? When we did 69 factorial, and we said it's approximately 1.71 times 10 to the 98th, didn't we just lop off 96 decimal places? So aren't we rounding about as extreme as you could consider? Lopping off 96 decimal places, that's not rounding? But what if I wrote that as a logarithm instead? Oh, then I wouldn't be bound by the whole 10 to the 99th power thing, would I? So, do you know what you do in real life? I'll give you a hint. You never, in a maths context, you never use scientific notation. I have to teach it in remedial algebra. I've never used it in any context in my entire life. But if I had astronomically large, I would use a logarithm. It's so much easier. And I'd use log base 10. Oh, so if the Richter scale, I got a 4 earthquake, I got a 5. Well, what about a 4.3? Can't I have a decimal? Yeah. Oh, so what does that mean? 10 to the 4.3 power, if I think about it in that term. Oh, there's nothing wrong with having a decimal. But I'm giving you a logarithm. I don't need an integer, and I'm not giving you, and the earthquake was, this times 10 to the 4th power. That's not incorrect. It's just completely impractical. But if I think in terms of logarithms, then there's no upper limit. So if my calculator, instead of a scientific notation answer, gave me a logarithmic answer. See, 69 factorial is approximately 1.71, right? Times 10 to the 98th. But what if instead I said this? Oops. What did I do? I just took the log base 10 of 1.71 and then I added it to 98, which is my exponent. Do you understand what I just did? Number times 10 to the 98th means if I do log base 10, it's 98 point something. Until I get to 10 to the 99, I don't have a 99 yet. If I wrote, I rounded to 3 places, but you know what? This is actually more, this is more precise than your calculator gave me because I went an extra place. This is the equivalent of log 69. Oh, so what if I want log of 1,000? What if I want log of 1,000,000? I could do the log base 10, but it's actually easier if I do the natural log, because the e is an easier thing to manipulate. But could I also do 10? Could I have done log base 10 here? And these would all be log base 10 numbers. And then my answer would be 10 to a power. Now, why would anybody use e instead of 10? You do the exact same thing using 10. Why would anybody use e? Think calculus. Derivatives and integrals of 10 to a power, derivatives and integrals of e to a power, which is easier.
E to the power.
E, yeah. For the sake of doing calculus, e is a lot easier to work with. But if I was only doing calculations, could I leave it as 10s? Everything I just said is true, but now you'd have log, 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 and then you'd have a different number, and your answer would be 10 to that power. So I want you to have a basic understanding of factorials, because there's no upper limit on a factorial, and you're doing problems where you're taking limits to infinity involving factorials. My calculator can only go up to 69. You know, last time I checked, 69 is a long way from infinity. Or they're really close together. I don't know. So when you reach 69 years of age, you're almost infinite then? I don't know. So we don't want to have limitations. So this is how we get around technology. And by the way, what I'm showing you has been known for hundreds of years. Did we have the ability to actually do the calculation though? No, only recent generations could actually do this calculation. Everything I've said is true, but the ability to calculate this, I still need technology to do this calculation, but this is a really simple calculation. This is kind of cool stuff, okay? So let's keep going. In the end, the important thing is to be able to categorize. So if I gave you a few series, yeah, tell me if it converges or diverges. That's the ultimate goal. But if I give you an integral, whether it's a Calc 1 integral saying, oh, it's one of these, or it's a Calc 2 saying, I need to use this technique, wasn't the most important thing figuring out what technique you're supposed to do? Or what's the form of the integral? Because if you can't tell me what technique to use, it's a parts versus a partial fractions versus a trig sub versus an evil trig. If I can't distinguish which types, then I can't start the problem. Calc 1, oh, this looks like a u to the n du. Oh, this looks like a trig function. Oh, this looks like an inverse trig. Oh, this looks exponential. Oh, this looks logarithmic. If I can't do that, then I can't actually integrate. Well, same thing's true now. When I look at a series, what do I see? Okay? So I'm going to give you a couple simple questions, and you tell me. I don't even want to know the answer. I just want to know how to do it. Let's thank you. Okay. I'm not interested in the answer. I'm interested in what technique would you perform, because if you perform the right technique, it is highly probable that you're going to get the answer right. If you perform the wrong technique, you're going to be, bashing your head against the wall over and over again because you reached a dead end. So, first one. There are like 5 different answers. So many in this row, I think, said. Limit comparison. And what would you compare to? Compare to the sum 1 over n, and you would use the limit comparison test, because the degree difference is 1, and when you do that limit comparison test, you're going to get, well, depending which one's on top, you're going to get either 3 over 6 or 6 over 3. Is that a good result?
Yeah.
Does it matter if it's greater than or less than 1?
No.
Not for limit comparison. It only matters that it's not 0 or infinity.
Right.
Now, here's the mistake a lot of us make. I'm going to do the limit comparison, and I'm going to put this one on top over the other one, which means I know I'm going to get 3 over 6. And when you're all said and done and you said the limit of your stuff equals 3 over 6, and that's less than 1,
No.
Oh my God. If you're using a limit comparison and you're comparing to any number, that means a right answer is sheer accident. I don't even want to say luck, it's an accident. This has no meaning mathematically whatsoever. Why? Because if I do it the other way, I'm going to get 6/3, which is greater than 1. Would that change your conclusion? No, you got a finite non-zero number is how you made your conclusion. This is the part I was talking about last day. This is where all the mistakes come in. Not that we do the wrong test, is we don't know how to conclude. So I'm going, regardless whether I get 3/6 or 6/3, depends which one I put on top. Both of them are finite and non-zero, which is a perfect result, which means my two series are acting like scalar multiples. So the behavior of one is the same as the behavior of the other. And by the way, what would my conclusion be? Converge or diverge? Because I compared it to something that diverged and it had the same behavior. Everybody understand that? That's the big picture. Okay, that's the huge big picture. Could I have used a ratio or a root test on this one? This is all really new, I know. Could I have used a ratio or root test? We used a limit comparison.
You can't use ratio because it's polynomial-ish.
So therefore, no. If I could use the limit comparison, that means I used what we learned last day. I said this earlier. Absolutely nothing we did today then would apply. It's impossible. Remember, we did a ratio test earlier on the harmonic and on 1/n², and it gave us 1 in both cases. For ratio and root test, 1 is bad. For limit comparison, 1 is wonderful. So, perfect answer. Next one.
Root test or ratio?
Root or ratio.
Get 1/2.
And it won't make any difference, will it? And what will I probably get in the end?
1/2.
2.
Probably gonna get a 2. Probably gonna get a 2, because that one's on top. I'm gonna do ratio or a root test. Most of you, because of the n cubed, and you don't like writing it as 3 over, most of you would probably do a ratio test, but a root test is absolutely valid on that one, okay? Oh boy. Can I do a limit comparison on number 3?
No,
Why not?
because it's raised to the n power.
No, because of the log. Limit
Well, I'm-
comparison only works on comparing to p series. I'm in?
For your last one, means n has to be started at 2.
Oh, thank you, yeah, thank you, you're right. Yeah. I was smart enough on that one to get, yeah, Min's right, it has to start at 2. I could use an integral test. And by the way, it's not the word, it would be an integration by parts, and it would not be horrible. Integration by parts involving logs, if you guys go back and look at it, they weren't that terrible. It's just that I'd have an improper integral that I have to use integration by parts on. That doesn't make me excited, That doesn't excite me. Yes, but is there something better? I can do a direct comparison test. What would I compare it to?
N over n cubed.
I compare it to n over n cubed or 1/n², and this is always smaller and it's positive. So I would do a direct comparison to this one. Because log n is always smaller than n, so log n over n cubed is smaller than n over n cubed. I have my inequality in the right direction. I made less than somebody who made a finite amount of money, but it was still positive. That's the correct direction. So that one, as awful as it looks, is actually a fairly simple direct comparison. Okay, next one.
Root test.
Can I use anything else?
No.
No. We did this problem earlier. This is a simple root test. What is your conclusion going to be? I'm not asking you to do the problem. I'm saying, can you see it right there in the statement? What do you think? Converge or diverge?
Converge.
What is the limit of your base going to be? And the base is that one. What's your limit going to be?
0.
It's going to approach 0.
0.
It's going to approach 0, isn't it?
Yes.
And what does that mean? That means my terms are getting small
Very.
really fast. If that ratio is approaching 0, that means these terms are getting microscopic. So yes, this will converge. In fact, it will converge very fast. That means if I just go out a few terms, I'm going to see changes later and later and later in the decimals that I probably only need a few terms to give a ridiculous amount of accuracy. That's what that tells me when these terms are approaching 0 really quickly. You say, well, why would that matter? Because not only is my base approaching 0, but then I'm raising that small number to a power that is growing without bound. Oh, see, these are not approaching 2/4 because of the degree difference.
Right.
Right, by the time I go out 10 terms, this is microscopic on the bottom. And I'm raising it to the 10th power. Meaning, I guarantee if you go out 10 terms, you have way more than 10 decimal place accuracy. Way beyond that. Okay? I cannot do limit comparison because of the logarithm, but I also can't do a ratio or root test because of the logarithm. Can I do a direct comparison? I'd need that power of n to not be 1. So what am I stuck with?
Integral test.
Integral test. But actually, that one's not bad. You know why? This is of the form 1 over u du. I think we did this problem last day, didn't we? So your integral is actually going to be the log of the log. That's going to be your answer, and then you're going to evaluate that. Is that going to be finite or infinite?
That's gonna be finite.
The log of n. Remember we played around with our calculators? I had you take n, as 10 to the 100th power, and then we still got a tiny number.
Yeah, it's gonna be.
But it's tiny numbers that are still growing forever and ever and ever, just really, really slowly. They're growing really slowly, but they never stop growing. They are growing very slowly. The log of the log is very, very slow, but it's still growing. That's the key. That's why we did that one last day, and I believe we got the diverged. So you've just done a really quick review of all 5 techniques we've learned. But the thing is, you learned a lot of techniques, but they really are quite distinct, aren't they? Now, I didn't put a factorial in any of these, but had I, what would you have done? Ratio and nothing else. Nothing else will work because the ratio test is how I eliminate the factorials. Okay, so let's do another one. All right. Let's do the sum from n equal 1 to infinity of, how about, let's do 1,000, oh, I'm sorry, not 1,000, n to the 1,000 over n factorial. Now, if I just write the first few terms, it'll be 1 plus 2 to the 1,000th over 2 plus 3 to the 1,000th over 3 over 6 plus, I think I see where this is going, 4 to the 1,000th over 24. It's getting kind of big. Okay. What test will we use though?
Ratio.
Ratio test. So I have the limit as n goes to infinity of. Now, be careful how we write it. Is this correct? N to the 1,000th plus 1.
No.
Is that correct?
No.
No. Is that a mistake we might make though? Yeah, because when I've asked earlier, I've gotten that answer hauled back. I'm replacing n with n plus 1. I'm not adding 1 to the quantity. So what should that be?
N plus 1 quantity to the 1,000th power.
N plus 1 quantity to the 1,000th power, and the denominator being
N plus 1 quantity.
quantity factorial. Now I'm going to be lazy and just multiply it by the reciprocal. Oop, inside there. Okay. Am I going to get cancellation here?
Yeah.
Different bases. No, I'm not going to get cancellation. But do I need them to cancel? The only thing I actually need to cancel are the factorials. If I had exponentials, I would hope they canceled also. Because I don't want a variable in my exponent. I want constants in my exponents in that case. See, these are constants. I'm okay. If these were variables, then I need variables in the exponents to cancel. So, what do I now have? On top I have n plus 1 to the 1,000th power. On the bottom I have n plus 1 times n to the 1,000th power. Ooh, this, I don't know if this is entirely obvious, but isn't the limit of a product the product of the limits? I saw somebody do this on a recent quiz. I thought it was kind of clever. They weren't sure exactly where to go, so they broke up the limits into bite-sized pieces. I'm not saying you have to do this, but I'm saying you might not see it otherwise. What if I rewrote this as 1 over n plus 1, and then multiply that by n plus 1 to the 1,000th power over n to the 1,000th power. Now, what is that limit? It's 1. Same degree, lead coefficients. Oh, that's 1.
And that's 0. So 0.
Wait a minute, but these were growing without bound. Yeah, until when?
Until you pass.
Until I got to the 1,000th term. When I got to the 1,000th term, they stopped, it flatlined, and then when I got to the 1,001st term, it was now smaller for the first time. Because that's 1,001 times the bottom, or that was only 1,000 times the top. So once you get to the 1,001st term, every term from that point on starts getting smaller and actually starts approaching 0. How fast? Well, I won't say very fast, but they're going to approach 0 over time. By the time I'm out 2,000, 3,000, 5,000, a million terms, these are actually quite small. Wow. Again, it doesn't matter what's happening in close. It only matters what's happening down the road. Got that? It's kind of cool, huh? Not hard, but different. Factorials are not things that we have a lot of experience with, and those who do have experience, it may not be recent experience. So if you're not entirely sure, just start from fresh. Start with what we're doing today. Factorials will come up a lot in the types of problems that we do over the next few weeks. Now, we have one more section in this stuff, but it's not a new test. We have 5 tests exactly, and you guys just did a great job of telling me which one's which, and that's the whole idea. If you can tell me which one, then you're probably going to do it correctly because you know which direction. Now, the only thing left to do is we're going to come back to every single problem, and we're going to make them alternate in sign. That's the whole point of the next day's lecture. It's a major, major theme. Well, what do I mean by that? I mean, we're going to do this. Positive, negative, positive, negative, positive, negative. And that actually changes things considerably. And I'm just going to give you kind of a hint. Every test we just learned how to do, we're still using those tests. But if I have a series that alternates, strangely enough, the things that right now are diverging might end up converging. Because if they alternate, think about it, I'm canceling roughly half the terms. Oh, so that might allow me, and that's why it's kind of cool. That's why we study them. And then once I have that down, now I can throw variables in there because that's exactly what the variables are going to do. They're automatically going to alternate. How do I know? Because if I put an x to a power and x is negative, it's going to go from positive to negative. And we really don't want to limit what types of numbers we can actually use. Okay, so we have one more section, but it's not new in how we solve problems. We're just going to expand the problems we looked at using nothing but the same tests. Now, I have posted the practice test some time ago. It might be a good idea before you come back to take a peek at it, but you don't need to because we still have one more section. I think our exam is like, what, 3 years from now or something? I don't know, some of you guys are going to have at least one birthday. It's a long ways away. But we only have one section left, so you can go a long way in your prep. Now, I say this in all seriousness, guys. This is a break coming up, okay? Actually, just stop that. This is a break coming up, and